भी करेंगे बाद में कि सिर्फ लाइव स्ट्रीम होगा? नेट ही स्लो चल रहा है। अपने को देखो
सोना
that continues to inspire generations of students and teachers. In this honor, we are privileged to have with us today Professor Murthy, Director IIT Hyderabad, who has graciously agreed to attend the event and deliver this information. Thank you so much. We begin our event by inviting the dignitaries, Professor Murthy, Professor Srivastava, Professor Singh, and Professor Srivastava to kindly come forward and offer floral tribute to Professor Srivastava and Professor Mahamanaji. Thank you so much, sir. May I now request all of you to kindly take your respective seats on the dais. Thank you so much, sir. I request our students to kindly come forward and offer the welcome bouquet to the dignitaries on the dais, please. Thank you, dear students. As a customary and honor the guest heritage of American University, I invite each of the participants to come forward. I also request those who are unaware to not clap after singing.
मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी ये तीनों लोकों से न्यारी काशी सुज्ञान धर्म और सत्य राशि बसी है गंगा के रम्य तट पर ये सर्व विद्या की राजधानी राजधानी मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी
नई नहीं है ये ईट पत्थर है विश्वकर्मा का कार्य सुंदर
रचे हैं विद्या के भव्य मंदिर ये सर्व सृष्टि की राजधानी राजधानी मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी यहाँ की है ये पवित्र शिक्षा कि सत्य पहले फिर आत्मरक्षा लिखे हरिश्चंद्र थे यहीं पर ये सर्व शिक्षा की राजधानी, राजधानी मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी, राजधानी
वेद ईश्वर की सत्य बानी, बने जिन्हें पढ़ के ब्रह्म ज्ञानी।
थे व्यास जी ने रचे यहीं पर ये ब्रह्म विद्या की राजधानी, राजधानी मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी, राजधानी वे मुक्ति पद को दिलाने वाले, सुधर्म पथ पर चलाने वाले, यही फले फूले बुद्ध शंकर ये राज ऋषियों की राजधानी, राजधानी मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी, राजधानी
सुरम्य धाराएं वरुणासी, नहाए जिनमें कबीर तुलसी।
भला हो कविता का क्यों न आकर ये बाग विद्या की राजधानी, राजधानी मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी, राजधानी विविध कलार्थ शास्त्र गायन, गणित खनिज औषधि रसायन, प्रतीचित राशि का मेल सुंदर ये विश्वविद्या की राजधानी, राजधानी मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी, राजधानी
ये मालवीय जी की देशभक्ति, ये उनका साहस, ये उनकी शक्ति।
प्रकट हुई है नवीन होकर ये कर्म वीरों की राजधानी, राजधानी मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी, राजधानी मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी, राजधानी मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी, राजधानी।
Thank you, student. With this, may I now request the Dean, Professor Srivastava, to kindly come forward for the welcome address, please.
Thank you. Good afternoon to all of you. Actually, I am representing Professor Upadhyay, who is currently Dean, but unfortunately, because of his father's demise 3-4 days back, so he is not attending any function. So I am representing Professor Upadhyay from the Institute of Science. So, dear Professor D.S. Murthy, Director IIT Hyderabad, today's speaker, Professor R.K. Singh, Head of Department, Professor R.S. Tiwari. I am seeing many senior colleagues that faculty members that Professor S.B. Rai, Professor Singh, Professor Joshi, Professor Madhurika Agrawal, Professor Upadhyay ji, Professor Lalan Mishra ji. So many are here. Esteemed colleagues, distinguished guests, friends, ladies and gentlemen. I heartily welcome you, sir, to the holy city of this Varanasi and this great institution, Varanasi University. On behalf of the university, the Institute of Science, and my own behalf, I warmly welcome you to this university and this Professor Srivastava Memorial Lecture. Today we come together to celebrate not only the enduring legacy of Professor Srivastava, but also the profound significance fostering curiosity and innovation in scientific research. Professor Srivastava was luminary in the field of physics, a pioneer whose contribution has illuminated path for countless researchers. His commitment to advancing science, his unwavering curiosity, and his dedicated to nurturing talent serve as an inspiration for all of us. He was really a role model for all of us. This memorial lecture is a testament to his remarkable contribution and an opportunity for us to reflect on the idea he cherished. Actually, on this occasion, I would like to share one small memory with Professor Srivastava. बहुत पहले की बात है जब मैंने जस्ट ज्वाइन किया था इस यूनिवर्सिटी को एज ए लेक्चरर, इसमें असिस्टेंट प्रोफेसर नहीं होता था, लेक्चरर, और मैं दिल्ली की यात्रा कर रहा था काशी विश्वनाथ एक्सप्रेस। तो मैं कभी उनसे मिला नहीं था, नाम जरूर प्रोफेसर श्रीवास्तव जी का सुना था लेकिन कभी मिला नहीं था। और लकली हमारी बर्थ और उनकी बर्थ आमने सामने ही थी और 2 बजे 2 बजे के आसपास वो ट्रेन चलती थी काशी विश्वनाथ, आज भी उसी टाइम से चलती है और सुबह दिल्ली पहुंचती है। और जैसे ही ट्रेन चली प्रोफेसर श्रीवास्तव जी ने अपना पूरा बैग खोला और उसमें से बहुत से कागज पूरे बेड पे उन्होंने फैला दिया और उस पर काम करना शुरू कर दिया। और जब तक मैं उनसे हमारी बात नहीं हुई, क्योंकि मैं कभी इनसे मिला नहीं था और मेरी हिम्मत भी नहीं पड़ी कि मैं उनसे बताऊं कि मैं भी बीएचयू से हूं और एक जो पर्सनालिटी होती है, और जब तक लाइट में वो काम कर सकते थे तब तक वो ट्रेन में बैठ करके वो कुछ न कुछ करते रहे। और जब हुआ कि अब नहीं, अब सब लोग सो रहे हैं 10 बजे 11 बजे के आसपास, तब वो सोए। तो ये डेडिकेशन इज वेरी रेयर, आई हैव नॉट सीन दिस डेडिकेशन। एंड अच्छी बात यह थी कि उसी साल उनको शांति स्वरूप भटनागर अवार्ड भी मिला। तो रियली ये पैशन होना चाहिए रिसर्च में, पर्टिकुलरली दैट आई शेयर द स्टोरी फॉर द यंगस्टर्स। ये पैशन होना चाहिए कि कैसे रिसर्च करते हैं। So I am coming to this lecture. So I am deeply privileged to welcome Professor B.S. Murthy, a distinguished scholar and visionary leader, as our speaker today. Professor Murthy's illustrious career and groundbreaking work epitomize the joy and fulfillment that come from the life dedicated to research. Hello. The fulfillment that comes from a life dedicated to research and experimentation. The topic of today's lecture, the joy of experimenting by a researcher. Really very interesting topic. So I really fascinating topic, I may say, and everyone is interested to hear you. That resonate with essence of scientific inquiry, curiosity, and the pursuit of knowledge for the betterment of the society. So as a dean, I have to introduce the Institute of Science also. You all know, just for a just sake of formalities, that I have to share that what institute is doing. That Banaras University has a great history. It was established by Bharat Ratna Pujani Mahamana Pandit Mohan Malviya ji on February 4th, 1916, almost 109 years ago. I think just next month we will be celebrating our 109th anniversary, that our foundation day. Although our institute is just 9 years old, but teaching and science started since establishment of the university in 1916. I think much earlier than that, but with the university established, the science education has started with the few basic subjects like physics, chemistry, and biology. Later, when it was recognized as College of Science in 1919, other science subjects also started. In 1968, it becomes the Faculty of Science, and just 9 years back in 1916, just 100 years after the formation of this university, it is upgraded to the Institute of Science. Currently, the institute has 13 departments, 2 schools, and 2 centers. In fact, this institute is larger than the many independent research organizations of the country. Currently, our institute has 328 faculty members. Sanctioned post is, I think, more than 350 or even more than that, and more than 6,300 residents, including undergraduate, postgraduate, and research students. Many faculty members are fellows of the 3 science academies of the country, 13 fellows of INSA New Delhi, 12 fellows from Indian Academy of Science Bangalore. This is currently in the campus, that this is not total number. 20 fellows from the NASI Allahabad and 3 fellows in the NAS. If I am correct, currently there are 6 JC Bose National Fellows also working in the university. And many faculty members also have many other prestigious national and international awards and recognition. List of distinguished alumni is very big, but I will take few names like Professor Santi Swarup Bhatnagar, Bebal Sahani, Bharat Ratna C.N.R. Rao, Jayant Nallikar, T.V. Ramkrishnan. I think these both are from the physics department. And Professor Lalji Singh, he was also Vice Chancellor of the Banaras University, and many more. This list is very big, so I am not going to take all names. Once again, I welcome you all to this Professor O.N. Srivastava Memorial Lecture. Thank you. Thank you very much. I think you will enjoy the lecture.
Thank you so much, sir. With this, I would now like to invite the head department president, Professor Rajesh Singh. Please kindly come forward and introduce the event.
Good afternoon to all of you. Honorable Director, IIT Hyderabad, Professor B.S. Murthy sir, Professor S.N. Upadhyay sir, former Director, IT BHU, Professor Madhulika Madam, former Dean, Faculty of Science, Professor Joshi sir, former Dean, Faculty of Science, Professor S.N. Thakur sir, Professor R. Shankar, Professor R.S. Tiwari, a distinguished professor in the Department of Physics, Professor S.P. Rai sir, Professor D.P. Singh. There are so many, Professor N.K. Mukhopadhyay sir. There are many faculty members from different departments of IIT, BHU, Department of Physics, and many other departments of BHU, and my dear students. For the first Professor O.N. Srivastava Memorial Lecture being organized by Omkarnath Educational Society and Department of Physics, in my opinion, none other than Professor B.S. Murthy would have been more befitting for a person like dedicated researcher like Professor O.N. Srivastava and dedicated and a very renowned researcher like Professor B.S. Murthy. Since I have been entrusted the responsibility of briefly introducing, since his CV is more than 50 pages, just I am going to give a gist in 3-4 minutes. Professor B.S. Murthy, for students, started his career, he did diploma, then he did B in 1986, Then in 1988 he did ME from IC Bangalore. Then in 1992 he did PhD from IC Bangalore. And then from 1992 to 2004 he was at IIT Kharagpur. Then in 2004 he shifted to IIT Madras in the Department of Metallurgy and Material Science. And then he was there, and in August 2019 he became the director of IIT Hyderabad. Now, he has been conferred with so many awards and distinctions. You can imagine that he is fellow of all the three national academies. He was J.C. Bose Fellow from 2018 to 2023, and he was Bhatnagar awardee. He was conferred this award in 2007. He has published more than 500 plus these 500 papers. He has produced more than 55 PhDs. He has been PI of more than 75 projects. You can imagine those who are sitting in the audience. Uh, yes, that's why I'm making it deep in the beginning, I said. So, since we are here to listen to Professor B.S. Murthy, and therefore, without going in any further detail, thank you all.
Thank you so much, sir. I think with this, I would now like to invite the speaker of the afternoon today, Professor Murthy, to introduce the joy of experimenting, what we have been always hearing, but today it is very explicit, and it's going to talk about joy of experimenting by a researcher. So, sir, stage is yours.
Good. Good afternoon, friends. I'm honored to have so many distinguished people in front of me. I feel like a Lilliput in front of all of them. A small nanoparticle. I worked on these nanoparticles. I know that they are important, but at the same time, I feel humbled to be in front of all of you, and particularly when I was invited to come for this particular lecture. Sure. Okay. Okay, he is of that kind of a person. In my group, we have a habit of going at 11 o'clock in the night for a cup of tea, the whole of my group. And those are certain things which I hear Professor ONS kind of legacy, I would say. So first of all, thank you for all those who have invited me and for the committee who has selected me to give this lecture, and I owe a lot to all of you friends. As I mentioned, I'm a metallurgist. I'm an experimental metallurgist. So I have been always joyful to do experiments, and I would like to possibly share some of my joy in experimenting variety of things. I have always believed in one thing, that for a researcher, it is important you keep moving from one field to the other at least once in 5 years, so that you learn new things. That's exactly what I have done in my life. So much to learn. The plate is never full, so you have a lot to learn all the time. So that's something which I have always believed in, and some of that journey is what I thought I will share with all of you. And some of those experimental, I would say, mentality that I have, I also possibly pursued some when I came to IIT Hyderabad as a director. Possibly if there is some time towards the end, I will also possibly talk about that, what kind of experiments that we have been trying to do at IIT Hyderabad. I'm a strong believer that education should be student-centric rather than you teach what you know. It is better to ask the students what they want to learn from you. So that is something we have started experimenting at IIT Hyderabad, and some of those tidbits I will possibly share as we go. So I just want to give you a few milestones in my life for the sake of youngsters to understand. I started my life with a diploma in metallurgy. I just finished my 10th grade. My father said there is a polytechnic in Vijayawada. That's the place where I come from. He said go and join. So I did not have any other word to say, because at least my generation, we just go by what your parents say. So, and somebody was telling those days that there is something called Vizag steel plant which is coming up, Visakhapatnam steel plant, that if you do metallurgy, there will be a lot of jobs. So that is how I chose metallurgy without knowing anything about it. A little bit that in 10th grade you possibly will know about chemistry, what is metallurgy, but nothing beyond that. But I met a great personality there by name Prof. Murthy, and he made me interested in metallurgy. That metallurgy can be interesting is something that I have learned from him. Then luckily there is a place called VRCE, which is now called VNIT, Visvesvaraya Regional College of Engineering, we call it as those days, had an option of a diploma person doing BTech and joining in a lateral entry mode into the second year BTech. Nobody else was taking. I mean, I finished my diploma, was a state ranker, and didn't know what to do. And that was the time one of my uncle sends me an advertisement of this VRC saying that they will take people into BTech. And that was a turning point in life, I would say. And then I met another great gentleman, Professor A.V. Ramarao. He made me interested to become a teacher. All those 3 years of my stay there, that interest becomes so strong that at the end of my BTech, unlike many other students, I clearly told I don't want to sit for a placement. I'm not interested to be placed. I'm sure one job will be waiting for me at some stage. That let me pursue what I would like to pursue to become a good teacher. So I asked Professor Ramarao, sir, what should I do to become a teacher like you? And he said, Murthy, you should do a PhD. That will widen your horizon, and you will be able to be better, a teacher if you do a PhD. And then I asked him, where, sir? He said, there is no place better than IISc Bangalore. Okay, so that's it. I closed my eyes, and then some seniors told that IISc is not an easy place to go. You have to, those days there was nothing called direct PhD. So you have to do a master's and then do a PhD, and there is something called a GATE exam. And somebody told, unless you have a 99 percentile in GATE, you will not get into IISc. That's it. My goal got set. So I worked very hard and got that percentile, whatever is needed, and entered into IISc. That's when I listened to a great gentleman by name Professor Ranganathan. So first lecture of him as an ME student, it was on what is called alloy design. Hmm. So he was very famous teacher for that particular subject. I still have the notes of that with me, and I was flat. I said if I do a PhD, I should do only with this gentleman, nobody else. And then somebody told that it is not easy to do a PhD with him. He takes only one student a year, and he should be the topper of the class. Okay, so that's it. Again, once again, a goal got set for me. So life is like that, friends. People, it's like playing a football. If you have a goal post, you know where to hit the ball. If you don't have a goal post, you don't know. You keep on, as हिंदी में बोलते हैं भटक रहा है. So you will keep on roaming around. So that's why in my life somehow these goals got set, incremental goals every time, and then I became a student of Professor Ranganathan. Today, what I am standing in front of you, to a large extent, largely because of him. He taught what it means by quality of research, that you should focus yourself in doing the most exciting research. I keep telling to youngsters, some of the youngsters being here, that to be called as a good researcher, in my view, there are three qualities which are very, very important. One is that you should be able to go for a cup of tea with your friend and talk about research. Not a new movie that has come, not about a cricket match or anything else. Second is you should be able to go to bed thinking about what problem that you are solving that day. It may be an experimental problem, it can be a theoretical problem that you are solving, and many a times you get solutions in your sleep. And I have a number of such incidents where I have felt happy to see a solution in my dream. And then a third and most important, I would say, you should be able to catch hold of a 12th standard kid and make him or her excited about what you are doing. If you can't excite a person who is not in your field, in my view, you are not excited enough about your own field. A person who is not excited about his or her research should not be in research at all, in my view. Okay, so I request all of you who are not yet excited about their research to start learning. First and foremost is that you are solving a problem which has not been solved by somebody else. Because if you solve a problem which has already been solved, obviously you will not get a PhD, right? So that means you are doing something new. That itself should give you enough of excitement. I am excited every day, to be honest with you. So every Wednesday I meet my PhD students. I still have about 8 PhD students. Night 8:30 these meetings start and go up to 12:30 in the night. And I keep waiting, when is the next Wednesday going to come. So that is the kind of excitement that I keep when I meet my students, so that I learn something new that they are going to tell me what they have done in the last 1 week. So obviously because of this responsibility, I don't get a time to meet them every day, but this once in a week I keep waiting. Then I finished PhD, then some 2 or 3 postdocs were there, but then IIT Kharagpur said they will offer me faculty position, visiting lecturer. No interview, just based on the CV that I have sent. And I asked my guide, Professor Ranganathan, sir, what do I do? He said, a bird in bed is better than 100 in the bush, please take it. You never know what will happen if you go for a postdoc and come back. That's how I landed up in Kharagpur, and then life started from there. Okay, as Professor told some time back, about 12 years in Kharagpur, 15 years at Madras, and all these years have been really, really joyful. Okay, and some of those joyous moments I will share with you as we go along. And first time I felt that the toughest time in my life was this, when I had to convince a team of people. I do not know if some of you have gone to Inside Scientist about presentation. Almost 15 people sitting in that room. There's only one material scientist there in that whole of 15 people. Somebody is a computer science professor, somebody else is mechanical professor, somebody is aerospace professor, and you need to tell them what is important that you are doing, how relevant it is, how important it is, and that was the time I have learned that it is important to be able to tell to a person who is not an expert in your field, who is not having any knowledge in your field, at the same time be able to convince them that what you are working is important. So that was an experience which I thought I should share. And then I moved to IIT Madras and got a good lab of my own. And the last one that I wanted to share, which is possibly the best moment of my life, not even Bhatnagar gave me that much of joy, when IAC said they wanted to give me Distinguished Alumnus Award. So the place where you study, you go back and that place says, like your father patting on your back saying that, yes, you are doing good. So that's something which made me feel very, very happy. So this is where I started my life. Okay, a field called mechanical alloying. I joined IIC Bangalore, and then finishing my masters. Those days it was 1.5 year masters, and I had to choose a problem for my master's thesis. And Professor Ranganathan is a person who does not give you any topic. He says, go and find out and tell me, and come back and convince me that that is an interesting topic. So I read a paper which talked about this. Basically, for some of you physicists, there are some things called alloys. Metallurgists deal with them daily, and these alloys are typically made by melting metals and then making them into a kind of joining with each other and forming various phases and giving you interesting properties are called alloys. And this is generally done by melting and solidifying. Whereas there is a field that has been emerging that particular time called, can I make an alloy in the solid state at room temperature by taking powders of different elements, bringing them together and then making them diffuse into each other at room temperature. Please remember, diffusion is the toughest process at room temperature. Diffusion is always a thermally driven process. Okay, and doing that, that was very, very exciting to me. And there was a paper in '83 where Professor Carl Koch from Caltech, he talks about NCSU, he is from North Carolina State University. He wrote a paper where a crystal can be made into amorphous by this process. Okay, so mechanical alloying process is where you put some powders into a basket or into a kind of container and hit them the powder with balls. When you are hitting with these balls, okay, there is a possibility of a lot of energy being pumped into this, and this energy can lift a crystalline material to a higher energy of state where it becomes unstable, and then it can become an amorphous state. So that was very, very exciting, that a crystal can be made into amorphous. And immediately I jumped and went to Professor Ranganathan. Sir, this seems to be very interesting. He is a crystallographer himself, we know. So when I said, sir, crystal can be made amorphous just by pumping in energy into it, he said, go ahead and do it. And that's where I started. And people started kind of ridiculing, because this is a system where you are hitting something with powders, with balls, and it looks very primitive. What is so great science in it? And then, so as a result, you always start thinking whether I am in the right direction or not. We keep hearing about quasi-crystals, same thing. Well, first time Dan Shetman was seeing 5-fold symmetry in front of his eyes in an aluminum manganese alloy in a TEM. Okay, he did not believe himself. And then when he started telling to people that there is something that I am seeing like this, his own boss, J.W. Khan, went to the extent to say, Dan, you are bringing disgrace to our group, please leave this group. Okay, you are talking something nonsense. Because 5-fold symmetry was known to be a forbidden symmetry. Many of you crystallographers know this. And here also, a few people tried that. Professor G.S. Shastri was one of them. In fact, 84, Dan Shetman published his first paper. 82, when he attempted, it was a failure. Nobody accepted the paper. Finally, 84, it got accepted. And in 78 itself, Professor G.S. Shastri published a paper which has shown a 5-fold symmetry in the alloy. So, but still, they also did not, I would say, dare enough to pursue it with a rigor that Dan has pursued. Okay, and there was a great chemist, Nobel laureate, who got 2 Nobel prizes, Linus Pauling, all of you know. He went to the extent to say there are only quasi-scientists and no quasi-crystals. So he took that ridicule also. And then finally in 2011 he gets a Nobel Prize. Possibly the only metallurgist so far who got a Nobel Prize. He is Dan Shetman. So this is something which is very important, friends. People sitting at the back, the youngsters, to know that when you believe in something, do not give up. Just go ahead and pursue your passion, pursue what you believe in yourself is. So that is something that mechanical alloying became almost like my life partner, and continued to work. And that was the time Professor Ranganathan was basically a crystallographer, and his thermodynamic knowledge was very little. And I was curious to understand under what thermodynamic condition a crystal can become actually an amorphous state. Okay, so I was very engrossed into it, that I was searching for who can understand a little bit of my thermodynamics. That was the time I met Professor Ramchandra once when he visited IISc Bangalore, and then when I explained it to him, he became very excited. He said, whatever you are doing, keep sending it to me. I will go through them and give you some comments. So those days there were not even emails existing. I'm talking of 88. So I used to send, make a lot of calculations and a lot of derivations, and a bunch of 10 pages or so I used to send him. He used to very patiently go through them and then send back his comments, and that's how my association with him started. And this is what is mechanical alloying, where you have a container where you put some metal and multiple elemental powders, and then put some balls and then rotate the whole thing. And in the process there is a lot of deformation happens, powders get fractured, and finally they end up into a nanocrystalline state. And that's something which drives the diffusion, because you all know diffusion is driven by a fixed first law, many of you are aware of. And if the gradient is very high, then the diffusion happens very fast. And to have the gradient very high, if your diffusion distance is very small, then the gradient is very high. So here in the process, because they are becoming nanocrystalline, then automatically the diffusion distances are very short, and then alloying happens at room temperature, which is something which is very difficult to perceive. And we have been able to demonstrate that almost every alloy can be easily made by this particular process, and there's a lot of exciting thermodynamics that one can talk about. So that was the kind of joy with which I have been pursuing. And then saw one day in my electron microscopy, those days Mukho used to teach me microscopy, and that is how we used to learn microscopy. So take a crystal and then demonstrate that it becomes amorphous just by ball milling it. Okay, so slowly the crystalline material, which is very clearly you can see the diffraction pattern, a crystalline diffraction pattern, slowly gets into a lot of defects get introduced into it, and a lot of distortions take place, and finally the metal becomes amorphous. The diffused halo that you see in a TEM is a symbol of an amorphous state. So that something was very exciting, and I was able to continue this in a number of materials, and then demonstrate that there is a critical strain that you need to put it into a material for it to become amorphous. And that changes from crystal to crystal depending on the type of crystal, whether you have a BCC crystal or an FCC crystal. The amount of strain that you need to pump in for a crystal to become unstable at some stage, because it cannot keep on accommodating more and more strain. At some point of time, this crystal with a lot of strain becomes unstable, and it prefers to become an amorphous state. So that was very exciting days. Then I moved to IIT Kharagpur, and there I met a great gentleman by the name Professor Masoon Chakravarti. He was a foundry man. Okay, if you have heard of this word foundry, we use in two contexts. One, the silicon foundries that people talk about, semiconductor foundry, but this is a typical metal foundry where the moment I joined, he told me, Prof. Murthy, I work on aluminum melting and casting of aluminum. There is a major problem that we face, that in aluminum, typically when we cast an aluminum, the grain size that you end up into this is very large, and because of which the mechanical strength of these alloys are very low. Can we think of some way by which we can improve the mechanical properties? I said, very simple, sir. You reduce the grain size, it should become high strength material. And then how do we reduce the grain size was an interesting thing. So there we have come up with a technology called grain refiners. Okay, I was more looking into fundamental aspects of what we call it as physical metallurgy, but I thought that the same physical metallurgy can be easily utilized in this to identify which kind of crystalline compounds are the right ones to nucleate grains in a particular metal, and that led to patenting, that led to technology transfers. So that was another exciting time that I had in the early stages of my stay at IIT Kharagpur, and we were able to convert metals which are of this nature. For example, if you take aluminum, cast a rod of aluminum, cut it and look at it in a microscope, you will see a grain structure like this. These are all called columnar grains. This kind of grain structure does not give you very good mechanical properties. But if that grain structure can be converted into extremely fine grains structure like this, it gives you extremely high strength. So basically the way we do is we add some particles which act as nucleating sites for aluminum grain to nucleate. There you need to understand a compatibility of crystallography between that particle and the aluminum crystal structure. So a lot of, again, crystallography knowledge that I was able to use, and finally we were able to get very extremely fine grain structures, and this has led to a lot of interesting applications and also a lot of industrial usage. And I will not go details into this. We were able to produce very high strength alloys and also introduce the same nanoparticles of extremely small particles to even create what are called metal foams. So all that was very exciting, mostly I would say industrial connection, and that's when my interest to develop technologies which are with very strong industrial applications became very passionate to me, and then a lot of patents came out of that. Then I started working with another professor by name Prof. I mean, those days Kharagpur was a place where the total number of PhD students in the department can only be 15. Okay, so we were 25 faculty members. So that means you have to share. Nobody can have an individual PhD student. Unless one PhD student finishes PhD, you cannot take one more. It is not 15 per year. Total were 15 on any given date. Okay, so that was the time, 1992, where I joined IIT Kharagpur. It continued for quite some time that way. So all my work at IIT Kharagpur was with two great gentlemen. One was Professor Bobby, one was Professor Mansunja Kurti. I had a few students that way, a few students here. And then we started thinking that how do we make nanocrystalline materials, and very, very exciting things that can happen. The moment you take a material into a nanocrystalline state, a lot of interesting things happen. Phase stability becomes a very important thing, and also what we call it as phase diagrams themselves start changing, and these are very interesting. For example, if you take any alloy, let's say aluminum iron, okay, and you start ball milling these two together, the moment they become nanocrystalline, suddenly you start seeing that one element starts diffusing into the other. Okay, that the so-called solubility of a particular element into other suddenly starts increasing the moment you go to a certain critical size, which is typically we found out to be around 20 nanometers or so. The moment you come to 20 nanometers size, suddenly you start seeing a lot of solubility being built up. So this is what we call it as, madam, if you don't mind, can you sit somewhere? You're standing. Sorry, if you want to stand still, you go ahead. I was a little concerned that you are standing. Okay. So many systems where usually for an element to dissolve into another, phase diagrams tell you that under equilibrium conditions the solubilities are very limited in certain systems. Okay. We may have even complete immiscibility of a particular element in the other, but we were able to demonstrate that once you go to a nanocrystalline state, you can change the solubility limits completely and be able to bring in alloys which are otherwise under normal equilibrium conditions you cannot make such alloys at all. So these are very interesting things that were exciting. This is one more such case. This is a nickel silicon phase diagram. If you look at it, there are so many intermetallic compounds in this phase diagram, but the moment you go to a nanocrystalline state, suddenly certain compounds which are formed by what we call it as non-congruent melting methodologies will become unstable. So you can only have certain compounds possible in a nanocrystalline state and which have very low interfacial energy, and those compounds which have a higher surface energy or interfacial energy become completely unstable. So a lot of exciting knowledge coming out where you start understanding what kind of phases are actually stable in a nanocrystalline state, what are not stable. So that was another very exciting journey which has led to a large number of PhDs in that particular period. Then I went to a place called NIMS. Okay, that was a time where for the first time almost most of you do a postdoc and then join a job. I did my first postdoc after almost 7 years of being an assistant professor. So that was the first visit of mine abroad for a long time. About 2 years I spent in a place called NIMS, which was those days called NRIM, National Research Institute for Metals. Anyone is aware of this place? NIMS? Okay, a few people I know. So this is, I would say, if you are not seen, if you are a material scientist, you should go to that place. This is one place which is possibly the best place for material science in Japan, and possibly in the whole world also, possibly one of the best places. And more importantly, having with a very limited access to microscopes. You know, at IISc Bangalore, we had EM301, 100 kV microscope is what we used to use. And there was a slightly better microscope which we used to call it as Professor C.N.R. Rao's microscope, okay, which metallurgy people were not allowed to use. so with that kind of constraint we used to work. And suddenly I go here, there are 15 TEMs in one building, a 7-storied building. Okay, and one microscope was given to me as if it is yours. You use it. Okay. So day and night I used to work on that particular microscope, and first time I started learning what it is called high resolution microscopy. Until then I never did that. And more importantly, first time I got introduced to a technique called atom probe tomography, okay, which is fascinating. Until then I used to think TEM itself is very fascinating, and the moment I started seeing that yes, you can see atoms in 3D inside a material was really very exciting. I was possibly the first Indian to have got a chance to work on the atom probe, and then since then I had this dream that why should such facilities be there only in places outside the country, and then every one of us have to keep on thinking of going there and use it. Can we not bring such facilities to India and make them available to our students, and so that they don't feel like going anywhere outside, and they think that all the best facilities that are needed for doing frontier research are available at our doorstep, is something that really was a dream for me, which I am able to now slowly realize over these last 10 years or so. And the main problem that I wanted to work on was those days there was a very interesting fight between two groups. One was a German group led by Jürgen Eckert and quite a number of other group members. Another group is a Japanese group which was led by one Professor Inoue. both used to report that if you take metallic glass, bulk metallic glass for that matter, and crystallize it, that one group used to say that if you take a glass and crystallize it, you get a crystal. Another group used to say that if you take a glass and crystallize it of the same composition, please remember, and it gives you a quasi-crystal. And nobody was able to understand why this group reports quasi-crystal, why that group reports a crystal for the same composition exactly. That was the time this Professor Hono and myself were discussing this, and I told him in a passing that maybe there is a lot of role being played by oxygen, because these are all zirconium alloys. Zirconium alloys can easily catch oxygen during the melting process. I said possibly oxygen is playing a role. And I said maybe one of the group is producing the alloys under a very highly controlled atmosphere. Maybe the other group is not so, and that oxygen is possibly playing a role and trying to stabilize a quasi-crystalline phase. So we wanted to prove this. So I took a zirconium alloy and added oxygen into it deliberately by adding zirconium oxide, copper oxide for that matter. It's a zirconium copper aluminum alloy, and copper oxide has the same melting point as the zirconium alloy melting point, so easily it dissolves into it. So you can deliberately add a certain quantum of oxygen that you wanted to add, and by doing that I was able to demonstrate that oxygen actually stabilizes quasi-crystal. This became a very path-breaking thing, and quite a number of people worked on it later. So this was a case where we have made 3 alloys. They are all somewhere, it's a zirconium copper aluminum alloy with different oxygen contents, and all 3 of them are amorphous in a XRD. You do TEM also, they will show you amorphous state. But the moment I start crystallizing them in a differential scanning calorimeter, you suddenly start seeing that the higher oxygen containing alloys show a small peak here, which says that a 2-stage crystallization, which indicates there is something happening there. And actually when you do microscopy, you will see the one containing less amount of oxygen shows a crystalline precipitates coming out of the glass when you heat them, and very clearly you can see that they are all crystalline. But the moment you take a higher oxygen containing alloy, they give you wonderful spherical precipitates which are all quasi-crystalline. You can see this diffraction pattern, the 5-fold symmetry and the 10-fold symmetry very clearly. And so this clearly says that the oxygen containing alloy gives you quasi-crystal. But we wanted to really see where is this oxygen going and sitting. Is it really going and sitting inside the quasi-crystal? So we have techniques those days, mapping techniques, elemental mapping techniques, but I am talking of 1999-2000 time frame, where most of the mapping techniques in the TEM are not able to see elements such as oxygen which have a lower atomic number. So I was not able to prove that, and then we said okay, atom probe can be the right technique to prove it, and we went into an atom probe. This is the best thing that we could get those days with a primitive atom probe, where you can see there is a small region here, okay, which has a lot of oxygen here. This is oxygen mapping, and these regions are depleted in aluminum and copper. Okay, this is a very primitive, I would say, a kind of a result, because now our atom probes are much better than these atom probes those days, but this was enough to really excite a large number of people, and it became a very fascinating paper later, and quite a number of groups started working on that. Then I came back 2001 and immediately went to 2 Banerjees. In India, 2 Banerjees, both metallurgists, are very famous Banerjees. Mukho knows them, but I think some of you also possibly know. One is called D Banerjee, one is called S Banerjee. Okay, D Banerjee, Dipankar Banerjee was heading DMRL Hyderabad, and S Banerjee, Sikumar Banerjee was heading Baba Atomic Research Center. I went to both of them. I was an young assistant professor. So I had the guts to go to them and say, sir, this is an exciting technique. and our research will significantly grow up. If we, I mean, in about 2 years, I was able to publish about 15 papers, all in real high impact journals, just using that atom probe. And so finally, Deep Energy got convinced, and he said, let's go ahead and buy it. He made me a member of the purchase committee. But by the time he was about to put an order, obviously different slabs take a long time, 2 years or so it took for placing the order. By the time a new model called LEAP came into existence, it's called Local Electrode Atom Probe. The original atom probe was called POSAP, Position Sensitive Atom Probe. For those who do not know about atom probe, I would like to say basically it's a mass spectroscope. Okay, where you make a sample in the form of a sharp needle, okay, and create a field at the tip of that, so that when the field is very large, the atoms can be pulled out of the particular metal. So once the field is greater than the work function, let's say, to pull an atom, and you have a detector in front of it, and this atom goes and hits the detector, and the distance between these two is well known. So once you know the distance, and once this atom goes and hits it, you know what is the XY coordinates of this atom inside the sample. If one layer of atoms are, let's say, sputtered away, and where it is hitting, that XY position will have a corresponding XY position in this particular thing, and the time that it has taken to reach the detector, because the distance is known, the time tells you about the mass of the atom. Okay, so basically these ions which are going and hitting, and from that you know which atom. So wherever a particular atom is located in a particular layer of atoms, you will know that this atom is going there, and layer by layer you keep on sending atoms, and then finally reconstruct the whole sample once again. And that's how you will be able to see that. And that was something which was very exciting. But then this new machine called LEAP was an American product, and DMRL, with all the restrictions that it has, they said, sorry, we cannot buy an American product. And I was urging Dr. Banerjee, but it could not work. Finally, he bought an older model, which is called POSAP, from France, but unfortunately the POSAP has the particular company, which is called Kameka, has not been able to support it, and finally it did not produce much papers out of it, and I could not unfortunately use it. That's the reason why I always believed that it is better to have such machines in an academic institution rather than a BARC or a DMRL. So I felt again lost, and then again, but as a person, I always say I am a person who never gives up anything. So I did not give up. I kept on writing proposals to DSC, and that equipment cost at least 25 crores, and DSC very faithfully used to return my proposal. So in 2012, we took one more initiative, organized a workshop on atom probe tomography, convinced a lot of big people, and then we said, oh, this time let us go as a consortium. So Mukho was a co-investigator in that project, and a number of people from various IITs I took and put up a proposal once again. Again, it failed. That was the time then I thought this is not the way. Then I should possibly make really partners in the process. So that's when I asked, one idea came to me that if it is a remotely operable microscope, then possibly people can send samples, and I will be able to provide a computer to them with the software, and they will be sitting in front of their computer and operate it. And that way they will feel as if they are owning that particular machine. With this idea, I asked that particular company called Kameka. So Peter Clifton was the main person behind that. I asked him, can you demonstrate whether this can be remotely operable? He said, Murthy, just give me 6 months time. I will work on it and come back. So exactly this date, August 25th, 2015, he was sitting in our seminar hall like this, connected his laptop to the machine which is sitting in Alabama, and was able to align the sample and collect the data. In about 10 minutes, we were able to collect 5 million atoms. Okay, and our director, Professor Bhaskar Ramurthy, was sitting in that. I invited him and I told him, sir, now that you can see that it works, can you please give me permission to go to various places? So I went almost to every IIT. For your information, I didn't come to BHU those days because I didn't know whether BHU would give me money. So, but I went to various IITs, and most of the directors used to say, first convince my colleagues in the department, materials colleagues. If they are convinced, then I will get convinced. So finally, about 6 IITs, 5 older IITs and IIT Ropar. These are the 6 IITs which gave me 2 crores each. Okay, and then there is an institute called ARCA in Hyderabad which gave me 2 crores. So with that 14 crores commitment, nothing in the pocket. It's a letter. Okay, with that letter I put up a proposal to DSC saying that can you please give me 25 crores more. With that we will be able to set up a center. And Professor C.N.R. Rao was the chairman of that nano mission. The moment I go, he is a very interesting person. He says, if you have a project proposal, you come with 5 slides. The moment you put the 6th slide, you will not get the project. Okay? So you have to explain everything in 5 slides. Okay? So that's why nowadays, whenever I am recruiting a faculty, I say 5 slides you have to explain to me what is exciting in your work. Otherwise, put a 6th slide, you are not selected. I mean, just joking. So that is how I was able to convince him and finally got the 25 crores. And we have set up the world's first remotely operable atom probe. And this particular atom probe is here. We call it as National Facility for Atom Probe Tomography, where almost 8 partners. We run it in 3 shifts. I have 3 operators who come in 3 8-hour shifts. Their job is to fib a sample. Samples come from various of these partners, and we put it inside the atom probe. Immediately that particular person through a WhatsApp or so is informed that your sample is in. Then you sit in front of your computer and start operating my atom probe sitting at IIT Hyderabad. So Madras. I used to tell them, treat this as your microscope sitting in our campus. And that's how I was able to run this. Even today, it has been running. In last 2017, we inaugurated this. And the moment this was inaugurated by the DST Secretary, Ashutosh Sharma, he immediately said that this is a right model. Okay, so from now onwards, anybody asks me a large amount of money, okay, I will say, bring some money, I will give you some money. So Sati centers have come now that way. When you people got your Sati center, that was in the first stage of Sati, where you were able to get a good amount of money. But by the time we applied for Sati, we have been told that unless you get 25% of the money, you will not get the remaining 75%. So now we have set up a Sati center at IIT Hyderabad with a latest model. This was 5000X leap, we call it as, where what we have at IIT Hyderabad now is a 6000 series leap. There are only 5 pieces of this in the whole world other than us. 4 are purchased by Samsung. They are in Korea, and they want to see when they dope any semiconductor with something, where is that atom going and sitting, they want to know. Okay, so that they know how the properties can be manipulated. So that is something which they have 4 of them. The 5th one is in no other place than NIMS, because that is where the whole atom probe tomography started. Hono is more or less the first person to have started atom probe tomography. This is a company called Chemica. EPMAs are also made by Chemica, same company. And then the 6th piece is sitting at IIT Hyderabad. None of the American universities have it. No university in the world has it other than IIT Hyderabad. Okay, so that's the dream of me in my life, to set up facilities where students should feel that yes, it is there with us. Okay, and we should be able to do frontier research. So I welcome all those of you whoever is doing some condensed matter physics where you want to do some material characterization. Feel free to come to IIT Hyderabad. We are now starting from next 2 months or so we are setting up what is called microscopy training school at IIT Hyderabad, where we want to conduct an online microscopy course where anybody in the country can register, and it's an online program. Typically, we want to start with PhD students to begin with, because those are the students who have more commitment to research. And if somebody gets a minimum A grade there, and we say you are welcome to come to IIT Hyderabad, stay for about 3 months, and we train you hands-on and give you a drive test at the end. And once you pass the drive test, you will get a certificate from us saying that yes, you are now an allowed official user of the microscope. And whenever you come back to IIT Hyderabad with a sample, you can just walk in and use the microscope without anybody being there. Okay, so that's fun. And we also feel that once you have been given such a certificate, when you come back to your place and wherever you have a microscope here, I hope your institute also will allow you to start using the microscope yourself. So this is something, this is first microscopy training school in the country, and what we have set up at IIT Hyderabad as a Sati Center is called In Situ and Correlative Microscopy Center. This is again the first such center in the country where you can do in situ experiments inside the microscope. Okay, you have a nanoparticles, let's say you want to see how do they grow when you heat up. Okay, you can see them growing in front of your eyes, and you can do growth kinetic studies to a large extent. For example, if you are a biology student, we know cancerous tumors. Okay, if you heat them at 50 degrees centigrade or so, they are supposed to be dying. So what is actually happening when you take a cancerous tumor and heat it to 50 degrees? You will be able to put your sample inside the microscope, heat it to 50 degrees, and see at the nanometric level what is actually happening in the cells. So all these can be done. You strain species, biological species or metallic species, and see what happens when it is strained at the atomic level. You can see. And we also call it as correlative microscope. This is, please understand, this is in situ microscopy at all length scales. We have a super high resolution optical microscopes, confocal, AFM, and then SEM and TEM. At all levels, you can do length scales. You can do in situ microscopy. You can also take the same sample, put it in different microscopes, and get different information from the same region, and get a comprehensive idea about the particular sample. This is called correlative microscopy. Again, possibly the first such center for a correlative microscopy, including an atom probe. So this is something we have been able to raise about 20 crores. This time I did not go to any IIT, even private colleges gave us money. And even pharmacy, Bharat Biotech gave 1 crore, Dr. Reddy's lab gave 1.5 crores. There is a hospital in Hyderabad called LV Prasad Eye Hospital. They gave us 1 crore. Every one of them are excited to use these microscopes. So feel free. Today morning only we were talking to your rector to have an MOU between IIT Hyderabad and BHU, and we would like to see if students of yours come to IIT Hyderabad and use these facilities. So that was another. This is one such sample. This is called ODS steel. We call it as oxide dispersion strengthened steel. All the pink dots that you see are all iron atoms, and where you see some green patches, there are 2 nanometer sized yttria nanoparticles. And within that particle, you can see which atom is sitting where. That's the beauty of these microscopes. And this is one such sample where you can actually see that this Li is a steel containing some iron, of course some tungsten, some chromium. The atoms are all uniformly distributed here. But the moment you see yttrium, titanium and oxygen, they are all segregated into these particular particles. So these are called yttrium, titanium, oxygen clusters, we call them. And these are very useful for high temperature applications of these steels. Normally a steel cannot be used at temperatures beyond 500 degrees, but by putting these kind of nanoparticles into the steel, we were able to raise its temperature capability to 700, 800 degrees centigrade. So that is something very exciting that we do. Then a new field that we have taken up, maybe 10 more minutes or 15 more minutes I will take, sorry, is this, what we call it as high entropy alloys. What is interesting is and gives you satisfaction is You start something and a large number of people start working. And in fact, mechanical alloying, we were possibly the first one to publish a paper 1990 from India, and now we see amazing number of groups working on this, even physicists working on, chemists working on it, and things like that. That was very satisfying. Again, this is another, the first paper on high entropy alloys from India is possibly ours, 2008 we started. We have what is called National Metallurgist Day, that we celebrate all metallurgy people once in a year, and that 2005 it was organized in IIT Madras. That was the time this gentleman by name Professor A came to IIT Madras and gave a talk on this special type of alloys called high entropy alloys. How many of you have not heard of high entropy alloy? Raise hands. Not heard of. Okay, so there are a few people. So let me tell you, these are basically alloys which are multi-component alloys. When you add a large number of elements into a particular material, okay, and if they are all, if you maintain equiatomic nature of the alloy. For example, I have an alloy containing 5 elements. Each of them is 20% each, let's say. So that means mole fraction of around 0.2 or so. So if you maintain such kind of a equiatomic nature, the configuration entropy of the whole alloy is very high. Okay, configuration entropy in an alloy is always a function of the composition. Okay, a dilute alloy will have a very low configuration entropy. A concentrated alloy will have a very high configuration entropy. And if the entropy of a material is high, then there is a tendency to have more randomness in the alloy. Okay, typically most of the alloys have a number of intermetallic compounds in it, and when the entropy of an alloy is very high, you tend to not get these intermetallic compounds. Instead, you get solid solutions. Okay, and solid solutions have better mechanical properties in terms of their ductility and strength combination, and that's why these alloys have become very exciting alloys, that for the first time you are using a thermodynamic concept to make alloys. Earlier alloys were all made to improve mechanical properties of material. I add this element, for example, take iron, put it outside, it just gets corroded. But then the steel plate that we eat every day does not get corroded. We call it a stainless steel. How did that happen? Just somebody came to know that if I put chromium into iron, this particular element brings in what is called corrosion resistance into the alloy. So that is how alloys got developed. When they come to know that one element will add value to the metal by adding, giving some additional improved property, people started making alloys. This is how alloys were conventionally developed. And most of the alloys that were developed so far are all what are called one element based. For example, steel. What is steel, friends? Anybody who is at the back can tell me. Alloy of iron and carbon. That's it. But do you know how much of carbon will it be there? Carbon, the best steels that we know. I mean, in fact, the definition of steel itself
keep on compound, and the angle of the industry should work to such an extent that at some stage the underlying compound is no more stable with the being built in, and it should become a that's exactly what we have done. We took a nickel titanium alloy. So these are all three interesting compounds. If you make these alloys regularly, they form ordered compounds. And the moment you take nickel titanium, add some lithium and hafnium into it, and take the nickel and no, kind of substitute a fifth of the nickel with copper. So it becomes a five-component alloy now. It's no more a binary alloy. And by making this into a five-component alloy, I have increased the entropy to such an extent that this becomes amorphous. So these are all very, very exciting things that have been, kind of taking me along. And then the final thing that we have recently came up with is, can we make alloys which can be used at high temperatures, but at the same time very light? If some of you have heard of that, the gas turbines that we use in aircrafts, okay, the turbine blades are made of something called nickel-based superalloys. Okay, nickel has a higher melting point, and if you have a nickel matrix in which you have an ordered FCC particles called gamma prime particles, such an alloy gives you very high strength at high temperature. So as a result, the turbine blades can be exposed to higher temperature. If you have heard a little bit on efficiency of a Carnot cycle in your school or somewhere, we know that efficiency of Carnot cycle depends on the inlet temperature and the outlet temperature. Okay, in an aircraft, the outlet temperature is not in your control. The inlet temperature. So if I can increase the inlet temperature, the efficiency of an engine can be increased. But to increase the inlet temperature, that means I want to set gases at high temperature into the turbine. Okay, gas turbine. There, the metals which are used as turbine blades should withstand those high temperatures. So that's how nickel-based superalloys were found to be the best alloys. Now we have come up with, for the first time, what we call it as aluminum-based superalloys. Typically, in aluminum alloys, you cannot have this kind of microstructure that nickel-based superalloys offer, where you have an FCC matrix and ordered FCC particles sitting as precipitates. Such a microstructure we were able to create using a high entropy alloy concept, and we were able to demonstrate that at 0.7 of the melting point of the aluminium, you can have 75 to 80% of the strength of what this material has at room temperature retained at such a high temperature. So this has been published recently, very exciting work, and a lot of applications we expect it to happen as we go along. I think with that, I will stop, and if you have a few minutes time, I don't know what is the time now, I can talk a little bit of experiments that I did. Do you have 5-10 minutes? Yeah. Okay. So one thing that, as I told you, I always believe that education should be student-centric. I have been in 2 older IITs, and I felt that somehow we are too straight-jacketed in our teaching. Okay, so I thought that let's bring in student-driven education. So first and foremost, I felt that if India has to become Viksit Bharat one day, okay, we need to have students who have a broader knowledge, and at the same time freedom given to them in learning what they want to learn. So what we started at IIT Hyderabad is interesting program. For example, we have a program called BTech in Engineering Sciences, okay, where a student for all the 4 years can pick up any subjects of his or her choice. Nobody defines what you want to take. You can take a few mechanical engineering subjects, few physics, few chemistry, few electrical engineering, few computer science. Everything is your choice, okay? And institute does not define. You will have a faculty advisor to advise you if you want to take his advice or advice. Otherwise, you can still go ahead the way you want. We also felt that when I was a metal with the student. All 4 years I studied only metallurgy, nothing else. Okay. So I said, let's give them a little more freedom. So at IIT Hyderabad now, we have revised our whole curriculum 4 and 5 years back to an extent that every student, every department, if you join as a BTech in mechanical engineering, okay, you can, the department can teach you only 60% of the total credits. Okay, we have about 130 credits a BTech student has to do. Out of that, only 60%, 72 credits alone can be done by the mechanical department. That includes 4 courses, electives, project, everything. The remaining 40% is in the hands of the student. Let the student decide what he or she wants to learn. Okay, because I always felt that I was telling in the metallurgy department in the morning that at 18 years of age you can actually decide who can be the prime minister of this country. Okay, so why can't you decide what you want to be in your life? Why should somebody else tell you what you should be in your life? So that I feel is very important. Give them that freedom. And at the same time, we also felt that we are too left brain centric when it comes to engineering. All of you know. Okay. And I strongly believe that life needs balance. So your right brain activity has to be inculcated into the student, which I'm very happy that in BHU you have a lot of arts schools, which in engineering institutions like IIT is very few. So we started saying that no undergraduate student at IIT Hyderabad will pass out unless they do 10% of their total credits in liberal arts and creative arts. Okay, starting from anthropology to psychology to philosophy to yoga to martial arts to personality development and music, dance, painting. We have a big basket of courses, and students pick up courses from these, and at least 10% of their total credits have to come from this. Otherwise, they cannot get the degree. So this way, we are one way forcing them, but at the same time giving them a big option of large number of courses, and the students love them. I mean, we have a Kathak dancer who comes on a Saturday, Sunday. These are all 1 credit courses for your information. IIT Hyderabad, we also felt that let us not have semester long courses, okay, which sometimes can be too long for a student. Instead, introduce a large number of half a credit, 1 credit courses. At IIT Hyderabad, for example, whole semester is divided into 6 segments. Typically, in a semester, we teach 3 credit courses. Many of you are aware. So the 3 credits is divided into 6 segments. 1 credit course, 1.5 credit course possible, anything is possible. Okay? So we tell our students, take a number of half a credit, 1 credit course in the first year. Explore and find out what are you liking. Okay? And then go deeper and take the 3 credit courses later. That also has a plus point for faculty also, because we typically expect a faculty to teach about 3 credits per semester. Okay? That means typically 1 course in a typical older IIT. 3 credit courses, 1 credit. Here at IIT, they can teach 3 1 credit courses. I teach 3 1 credit courses in the first 1-2 segments. Okay? In the month of August. At the end of August, my course requirement is over. I can happily go somewhere, sit there itself, do research the way I want to do. Okay, so a lot of freedom comes to the faculty that way. So this way we introduce this faculty. This is the only possibly academic institution in the country which has practical academics. Okay, no other IIT has, no other engineering institution has this. So we have been able to experiment it and make it very useful, and quite a number of students love it. So I was talking about this dance course, that Saturday morning 3 hours, afternoon 3 hours, Sunday morning 3 hours, afternoon 3 hours, 12 hours of teaching means 1 credit course. Finished over the weekend. And students love it. 500 students attend these courses. Okay, and these are all credited courses, mind you. Okay, so we were able to bring a lot of such transformation and ensure that students have a lot of flexibility. We went one more step further. We said students also should be given a lot of chance to work on their innovative ideas. So every semester we call for proposals from our students. We call them as build projects. Bold and unique ideas leading to development is the name we gave. So we ask the students, do you have any nice ideas to for any product development for the country? Okay, and if the students come up, typically we have at least 100, 200 proposals come every semester, and we give at least 50 to 60 of them. We have a committee which selects them, and we give 1 lakh to 2 lakh rupees to begin with. Okay, and provide a mentor. We have built a building, 1.5 lakh square foot area building we have built. We call it as TIP, Technology Innovation Park, where we give freely space to the students. We also tell them that I give you a semester break if you want to work on your innovative idea, so that you don't get disturbed from courses. Okay, 1 full semester they can spend on that. We give 6 credits for it. Okay. In fact, a first semester BTech student can take a semester break at IIT Hyderabad. It doesn't happen anywhere in the country, I can say. Okay, we were able to do this. And we said, 2 years of 11th and 12th, you are all in coaching centers, got spoiled enough. Okay, but you may have a great innovative idea, but you never had a chance to implement them. So come here and implement. And to implement that, we also did one more thing, that we removed what is called branch change option. Okay, at IIT Hyderabad, once you join a particular branch, you can't change the branch. But at the same time, because flexibility is important, I said we will create what is called double major in every branch of engineering. So that means you join in the mechanical department, at the same time you can get a double major in computer science or AI or any other subject like physics, for example, just by doing 24 extra credits. And in the 4 years, you get the 2 certificates. We also said if a student is brilliant and he is able to take extra credits every semester, okay, and be able to complete all the 130 credits by the end of 3rd year, we said take the degree and okay, you don't need to stay for all the 4 years. Okay, so we have also created this. All these are Senate approved. Okay, we got the approvals of Senate, whatever you call it as in your place, we call it as Senate at IIT Hyderabad. So this is how we were able to see that we create an ambience there. And students, I tell them that now that you don't have a branch change option, typically every IIT student, particularly branches like mine, metallurgy and course. Okay, students who are sitting in the class, they feel as if I have done my JEE slightly better, I will not be sitting in this class. Huh? That is the kind of students we face. And those guys, first year, they have worked very hard to get a 9.5 CGPA to stay in the branch. Okay, and we say, let us avoid this. And many of them don't get the branch change. Okay, what do they do? 3 years they crib for the remaining 3 years and go out and join some software job finally. So we said, let us not have all these problems. Let's tell them that you have joined. This is what possibly God has given you. Okay, start seeing whether I can enjoy that. Okay, everything can be enjoyed in life, and like every part of your body, every organ of your body is equally important. Every branch is important. Okay, for example, India, if it has to become Viksit Bharat, if you think that by just becoming a computer science fellow, I will make India Viksit Bharat, it will never happen. I'm very clear about it. So it is important that we should focus on manufacturing, we should focus on product development, and that's something very important. So when we started doing all this, we also said at the end of 2nd year BTech, if your ideas are working well, okay, you go out now, start your company. We give you a diploma. Okay, and then we say that we give you 5 years time if you want to come back and complete the remaining 2 years and take the degree. But I'm very happy if a student after 2 or 3 years comes to and tells me that I don't need your degree, I'm already successful and my company is doing very well. I feel that is the kind of students we should produce it for the country. If India has to really become a Viksit Bharat, for me, a Viksit Bharat is a day where I go to a place like Melbourne or somewhere, let's say Berlin, and go to a shop and buy a product and see what is written on the cover. I should see made in India. Okay, the day I can see that, I would say India has actually become developed. And how can that happen? Only when youngsters like all of you, okay, decide that I should focus on technologies. I should spend more time on what is called research. and technology development. In fact, recently, in the last 2 years, we have signed an MOU with 10 NITs. I've been observing that NITs, typically, every student at the end of 4 years, they just want a software job and go, irrespective of whatever branch they study. Okay, as people say, all roads lead to Rome. Okay, so all the students move. So I said, can we not bring them and make them excited about technology? Okay, and we now, last year, we got about 30 students to IIT Hyderabad. And we say that you don't need to pay a single rupee to us. You pay the tuition fee back to your NIT. You do the same number of credits which you are supposed to do there. We transfer the credits. You get a degree from there. But full year, you do research along with your courses. In fact, on the iSTEM portal, which you probably are aware of, IIT Hyderabad has put about 480 equipment on the iSTEM portal. One of the largest possibly by any institution. We have so many of these research facilities that we have set up. We said, use these facilities and do some good work. And at the end, we saw that out of these 30 students, 20 stayed back with us for PhD, 5 started their own startups, and the remaining 5 went on. Okay, this year we have taken 100 students, 10 each from each, and we want to see how we can transform some of them. In fact, in the last 5 years from IIT Hyderabad, we have close to 250 plus, I would say, startups that have come up, and they have created a revenue of 1,500 crores of revenue. So that's the kind of amount of money that they are creating. So these are all undergraduate students to a large extent. A few of them are postgraduate, of course, mentored by faculty. Okay, so this is possible, guys. So I think that's the kind of students that we should be able to creating. I would like to see students at the end of BTech saying, I don't want to sit for placement at all. Okay, I would like to create jobs for people rather than seek a job. And that's the kind of people, if we can create, India will be mixed. Okay, so those are certain experiments that we have been doing, and many of these are really working out well. We are very happy with them, and some of those are what. One more thing, possibly the last thing that I want to say is that last 2 years we have also started saying, why don't we teach the whole world? Can we become Vishwaguru? Okay, so this is a concept. India was known to be a Vishwaguru once upon a time. People used to come to, Nalanda Takshashila is what we used to hear. Now we say, use the technology and ensure that you reach out to people. I am a believer that education and learning should not have any constraints. For example, if I want to just do one course on quantum mechanics, and that there is a professor teaching, I am sitting somewhere in some corner of the world. I should be able to learn from that professor. Okay, with the new technology that is available, without physically coming and sitting there. But unfortunately, in India, just to do one course also, you need to register for a degree, and then they will ask you what entrance exam you have written, what is the background degree that you have, and many a times in that degree, some of the courses I don't even like, but I have to study them. Okay, instead we are saying now that you just register for individual courses. I just want to learn one course on astronomy, let us say. Okay, there's a professor at IIT Hyderabad, let's say, teaching astronomy, and I just register. So we converted all our classrooms into hybrid classrooms. I have physically a few students in front of me, virtually a few students on the screen. But whatever I write on the blackboard, they are able to see what I write. I'm a blackboard teacher still. I teach a course every semester. I teach a course typically in the evening hours, 6 to 7:30. Just the course that I finished last semester, I had a few students from various European countries also. One from Sweden, one from Berlin, one from even I think Malaysia. There are quite a number of students sitting like that. And regular other students of our own institute sitting in. So this is like a live learning. You are inside the class almost. You can see what teacher is teaching you, and you can ask questions. The faculty answers, and whatever are the questions that are being asked by the students who are physically there, that also the online student will be able to hear and learn from what they are asking, what the answer teacher is giving. So this is first time I would say, an experiment that we have done. We have about 15 courses running like that, which we call them as OAT, Open to All Teaching, and we charge 5,000 rupees. Okay, that's what we charge for the course, and we say let anybody learn. We say it can be a student, it can be a professor, it can be a working professional, it can be a homemaker, it can be 80 or 90-year-old man or woman. Let anybody learn. I tell my colleagues, don't control the exit entry, but only control the exit. Okay? Because most of the time we only control the entry to a large extent. So many entrance exams that we have, making the life really very difficult for youngsters. Instead, let anybody learn. Hmm? And I'm not giving a degree at the end. I'm only giving them a certificate that you have done this course. So as a result, JE does not come into picture. Nobody comes into picture. Ministry does not really create any problem. So we were able to start this, and this is working out very well. So I just wanted to share these things with you to say that it's time, friends, that we need to bring in a transformation in the way we run education institutions and make sure that the students learn what they want to learn. Okay? And at the same time, make sure that you bring out programs which are useful for them. For example, 2022, first, our Prime Minister has announced India Semiconductor Mission. Immediately in 3 months, we have a BTech program started running on August 1st, which is on semiconductors. BTech in semiconductors. We don't have any such program anywhere in the country till then. We said, let's start. If a fab is going to come, where are the engineers? We have only electrical engineers, we have only CE engineers. We don't have engineers who have a knowledge on semiconductors. So we thought, let's start that. In fact, on that day, I met a very famous professor by name Professor Rao Tumala. He's from Georgia Tech. He's known to be a father of packaging, semiconductor packaging. He told me, Professor Murthy, 35 years I have been working in this field. I have more than 100 patents. But in Georgia Tech, I could not start a master's program on packaging. Can you think of this? Immediately, I told my colleagues, and they were so excited about it. In 3 months, we were ready with the curriculum, we got it approved in the Senate, advertised it, shortlisted the candidates, and 25 students were sitting in the class on August 1st when the first class started. On packaging. So it's called MTech in packaging. So like this, there are many, many things. We also felt it is time to go and start collaborating with people. Okay, we have a program now with an eye hospital. We call it as MTech in ophthalmic engineering, where doctors teach the anatomy, physiology of the eye. We teach optics and lasers. Okay, and after 24 credits of theory being taught, the student does a joint project. Okay, at the end, the student is a laser expert for an eye care industry. So, variety of such things are possible, and I think it is important that strong collaborations need to be brought in by people, and where the collaborations do not exist so far. For example, technologists and healthcare people were always separated. There was never a strong collaboration. We started bringing a number of such programs. So with these few, I think, experiences that I have, I would like to thank once again to all of you for giving this opportunity, and wish all of you all the best, and see if some of you can visit IIT Hyderabad and see how we can collaborate with each other. I'm a strong believer that there is the only way to grow is through collaborations. Okay, that brings a lot of synergy and makes 1+1 significantly greater than 2. So let's work together for a better future of India and to make Viksit Bharat a reality. Thank you.
Thank you so much, sir. Initially, I thought it was a lecture on exploring and experimenting, but later I realized it was about everything. So I would request one more round of applause. I would now like to request Professor Aris Tiwari, sir, to please kindly come forward and thank the speaker by offering a moment and I would also request Dean sir and head sir to please come forward, sir.
सामने आ जाइए टेबल के सामने
So, okay. I kindly offer one of thanks, please.
Guru, they have asked me to job. So it's really a pleasure, and after listening such a lucid and very interesting lecture by Professor Murthy, uh, there is not much to say, but really it was a very befitting lecture in the memory of my Guru, Professor Srivastava, whom we used to say boss. He used to say, sir, sir, but then here everybody was saying boss. So we also started saying boss. So it's a really very befitting lecture. And as I said, that Professor Onius was very keen in every time he was always keen in developing the department and doing research and encouraging us, everybody, all his students to do research very intensely. And that is what we have learned from this lecture, that the excitement he wanted to share the excitement of the various research topics. For example, he started with the quasi crystals and then um, allies, what you call as the high entropy allies and so on. So it was a very, very interesting, and since I'm on the field, similar thing, so I really appreciated many interesting microstructures and the possibility that the technology has brought. Now you have many tools and many techniques through which you can explore and what is actually happening, what is going on, where elements are going and sitting and so on. So you have seen the excitement. So that is the pleasure that one gets when one is involved in research. And in that way, it is a very inspirational lecture for those who have just recently joined, because they will find that it's a really pleasure if you learn things and then you ask things and then you try to seek answer. So that's very interesting. So at this occasion, I would like to now extend my hearty congratulations and thanks to Professor Murthy for coming over here and giving this very, very interesting lecture. Thank you very much, Professor Singh. Now I would like to, it's my duty to thank Professor R.K. Srivastava Dean. He came here and participated in this program. He encouraged us. Our head of the department, Professor R.K. Singh ji, who always he was ready to help us in every way, and he very much encouraged us to recognize all this. We are very thankful to the faculty of the Institute of Science, PHU, as well as IIT PHU, students, researchers, and faculty members. They have come here and they have made this program very successful. And as I said, that this was what Srivastava used to think that there should be very always some inspiring lectures, some what is going on, what is new. So in that direction, we are remembering him at this moment. So on behalf of all of you, I thank you, Professor Murthy, and thank you very much.
It's just impromptu addition. Actually, just I wanted to mention here that the O.N. Srivastava Memorial Lecture was taught by and organized by Professor Anjay Srivastava. We were supporting the student Professor O.N. Srivastava. Four of us are here, and many of are in different places. So we collaborated and thought that it's a very appropriate that we start a series of lectures in memory of Professor O.N. Srivastava, uh, and we planned that we organize it in the third Friday of January, every January. So that is how this is the first lecture of the series, and we are very honored that Professor Murthy came here, and I hope that in the future also we get such illustrious on different groups. Thank you very much. बाहर चले गए लोग कि अंचल यहीं बैठे
बाहर जाएंगे, we can go outside for high tea, but before that I would request all of you to kindly stand for national anthem.